All right, so last section we are going to take a look at this week is 6.5. And 6.5 is on basically what we call right triangle trig. Okay, working with an acute angle and a triangle in order to figure out different things about the triangle. Sometimes we're going to look for sides, sometimes we're going to look for angles. So first, we'll start out with what a right triangle is. Okay, it's basically a triangle that has a 90-degree angle. Does anybody remember what we call the side across from the 90? What's the name of that? Yep. Hypotenuse. And what's the name for the other two shorter sides? Yep. Legs. Yep. Does anybody, you don't have to use these letters, but does anybody know the letters that we normally use when we're labeling the sides of a triangle? And we don't know the sides. Like what do we use for the legs? Start with that.
A, B.
A and B. Yep. And for the hypotenuse?
C.
C. That's just kind of the convention we use because there's a theorem that a lot of people remember, and it uses those same letters. What's the theorem that we can use in a right triangle, and it gives you a special relationship between the sides, but it's only in a right triangle. Yep. Yeah, the Pythagorean theorem. And do you remember what that theorem is?
A squared plus B squared equals C squared.
Yep. Just make sure we understand that A and B are legs, C is the hypotenuse. Why does this angle, we'll call them like angles 1 and 2. Why do angles 1 and 2 always have to be acute? Yep.
Because a triangle has to add up to 180 degrees, and one of them is 90 degrees already.
Right. So the angles have to add up to 180. You've already used up 90 for that. So the other two together have to add up to 90, which means each one of them has to be acute. If one of them was not acute because it was more than 90, the angles in the triangle would add up to 180. All right. So that's our Pythagorean theorem. Why? Why does a squared plus b squared equal c squared? Anybody know? That's kind of important to understand. Why a squared plus b squared equals c squared? There's lots of ways to understand it. Probably 20 different ways you can do it. But we're going to look at that picture. And that picture is going to tell me why a squared plus b squared equals c squared. So what I've drawn there is a big square that has a side length of AB. And in it, I've put a smaller square with side lengths of C. And by putting that square kind of rotated a little bit, it creates 4 triangles. And each one of those triangles are thinking of a word that describes how they compare to each other. Yep.
Congruent.
They are all congruent. Yep. They each have exactly the same 3 side lengths. All right. So let's see if we can figure out why a squared plus b squared equals c squared. Let's find the area of the square inside. Can somebody give me one way to find the area of the square that has a side length of c? Yeah.
C squared?
Yeah, it would just be c squared. Okay. I think to make this a little easier to talk about, we'll call it the green square. Okay, so we'll say area of green square. Method 1 is just to multiply c times c, because it's a square, and the formula for a square is side times side. Any question how we got c squared for the area? Okay. Now, I want to think about finding the area of this red square as a way to get the area of the green square. If I had the area of the red square, what could I then do to get the area of the green square? pretend like that red square was a piece of paper, and I said, I want you to turn that piece of paper into something that's the size of the green square. What would you do to it? Yeah?
I'd fold up everything in red to make the little green square.
So what, you explain it again?
You fold like the little corners in, all that type of stuff to make the green square.
Yeah, we fold the corners in, right? Or cut the corners off.
Yeah.
So, does that give anybody a hint? If you had the area of the red square, how could we get the green square? Yep.
So we would subtract all the areas of the triangles.
Right. Subtract the area of all the triangles, and we know they're all congruent, so we just find the area of one of them, multiply it by 4, and that would give me all the areas of the triangles. And if I cut that out from the green square, or from the red square, that should give me another way to find the green square. All right, so let's try that. Okay, so first we need the area of the red square. What's the length of a side in the red square? Yep,
A plus B.
A plus B. And in order to find the area, I need to multiply side times side. So it's A plus B times A plus B. And now we're going to subtract the area of each of those triangles. And there's 4 of them. So we're going to subtract 4 times the area of the triangle. And I'll label it. Area of the triangle. This is the area of red square. All right. What's the formula for the area of a triangle? Yeah?
To use the examples that we have, A times B divided by 2.
Yeah, it's 1/2 the base times the height. So it doesn't matter which one you look at. Think of B as your base, A as your height, and if you do 1/2 base times height, that's the area of the triangle. Don't fill in BH, put AB, because those are the letters we used. 1/2 base times height. Let's do that out. And whatever we get there, that's another way to find the area of the green square. Right. What do you get when you do A plus B squared?
A squared B squared? Or A squared plus B squared? No. Never mind.
What's A plus B squared? Yeah.
A squared plus 2AB plus B squared?
Yes. Good. A squared plus 2AB plus B squared minus what's going to be subtracted when you multiply 4 times 1/2 AB? Column?
2AB.
Yeah, I'm going to subtract 2AB. Now I want to figure out what that simplifies to. Stephen, what does that simplify to?
A squared plus B squared.
So that simplifies to A squared plus B squared. That's the area of the green square. Okay. So now, what can I do from here? Yeah.
Set the C squared equal to A squared plus B squared.
Yeah. C squared is the area of the green square. A squared plus B squared is also the area of the green square. Since they are the area of the exact same thing, they must be equal to each other. So A squared plus B squared equals C squared. So that area equals that area. And that's one way you can explain Pythagorean theorem. And just make sure you're clear about what A, B, and C are. A has to be a leg, B has to be a leg, and C has to be the hypotenuse in your triangle that you're working with. question on that? Okay, so now we know why a squared plus b squared equals c squared. All right, so next, we're going to look at the 6 trig functions. We've already looked at them when we did unit circle trig. The difference this time is we are not going to define them as with a coordinate. That's how we did it on the unit circle. We had like sine was y, cosine was x, tangent was y over x. Now we're going to define them as a fraction of the length of 2 sides in a triangle. So we should know what hypotenuse is, but if you're not sure about opposite and adjacent, I'll explain what those two mean. So each trig function in this section is going to be defined as a fraction or a ratio of one side of a triangle divided by another side. So take, for example, let's say you had an adjacent side of 4 feet, and you had a hypotenuse of 5 feet. When you divide that, what happens? Thinking more about like the final answer. What's going to happen in that fraction? Well, what's my unit going to be on the final answer? Yeah? No, not feet. Yeah?
You won't have a unit.
Won't have a unit. When you have feet divided by feet, it's gone. That's why when we do trig, we don't even worry usually about the unit because that's not important. When you have a length divided by a length, the answer that you get in that spot right there is a pure number with no unit, no label. This has a unit. That's an angle. Okay, when we fill in for an angle, yes, we have degrees or radians. But the answer we get after we fill that in and calculate it out is a fraction that has no label. Okay? So sine is the opposite over the hypotenuse. Cosine is the length of the adjacent over the length of the hypotenuse. And tangent is the length of the opposite over the adjacent. Now, when I put those 3 next to it, what's the connection in each row between the one on the left and the one on the right? Yeah?
They're reciprocals of each other?
Yes, they are reciprocals. They've always been reciprocals, and they're still reciprocals here. So based on that, what do you think the formula to calculate the cosecant is based on opposite, adjacent, and hypotenuse? Yeah?
Hypotenuse over opposite?
Yep, hypotenuse over opposite. And the formula for secant would be, yeah,
Adjacent over hypotenuse? No, sorry, hypotenuse over adjacent.
yep, hypotenuse over adjacent. And the last one would be adjacent over opposite. So there's still the reciprocals, just like with unit circle trig. Now, one way you can remember, if you've seen this before, Sakatoa. Anybody seen that before? So it just stands for sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. Okay, one time I had asked, is there a word or something you can use to remember those 3 trig functions? And somebody said Sacagawea. No, she's not going to help you remember. But Sakatoa, that'll help. Okay. And then if you remember the first 3, you flip them and you get the next 3. Okay. There's your 6 trig functions. Any questions on those definitions? All right, so now I'm going to explain what is opposite and adjacent. Well, opposite and adjacent are not fixed. They're what we call relative. So an example of something that's like relative in this room would be the words left and right. I couldn't label a wall and say that that is always the left wall in this room, because it depends on which way you're facing. Right? For me, left would be the door. For you, that would be right. So it's relative to your perspective. That's how opposite and adjacent work. They are relative to a perspective. So how do you know what the perspective is? Well, what they will do is in the triangle, they will mark one of the unknown angles. And the question would usually say from using theta, or like from the perspective of theta, what side is opposite? Opposite is always farthest away. Think about if somebody's opposite you, right? They're on the other side, like opposite side of the road, across from you. Adjacent means right next to you. If something's adjacent, it's right near you. So adjacent is the side that's right next to the angle, but not the hypotenuse. The hypotenuse is always across from the 90. So in terms of like directions in this room, like up. Up would be the same no matter which way you're facing. Face this way, up is the ceiling. Face that way, up is still the ceiling. Now if you take same triangle, but they shift the perspective and say, okay, now pretend like you're standing there and you're looking out at your triangle. Opposite is the side that's furthest away. Now the bottom is opposite. And the height is the adjacent. Okay, so opposite and adjacent switch places depending on which angle you're dealing with in the triangle. Questions on that? So I think we mentioned the term congruent earlier. We didn't mention this term, similar. There's a difference between those two terms. Congruent means you have two shapes that are identical. Like if you draw a shape, put it on a photocopier, hit copy, you get an exact copy of it. There's no change in this, as long as you don't change the size. Similar means you've changed the size. Okay. So the question I want to look at is, if you're working with a similar triangle, would it change any of these answers? So like if you had a triangle and you found, say, the sine of that angle, or we took that, made a larger version of it, and now found the sine of that angle, would it change the answer? Well, the side lengths are definitely different. Right? The opposite and adjacent side are larger here than they are here. But what do we think? You think it would change the answer? Yeah?
No, because the change was proportional.
Yeah, it's a proportional change, so no, it doesn't actually change the answer. So that means if you are working with a 45-degree angle, or any angle, and I say find the sine of 45 degrees, it doesn't matter how big of a triangle you have. You could have a really small triangle with a 45 in it. You could have a huge triangle with a 45 in it. It's not going to change the answer for the sine of 45 degrees. A given angle will always have the same trig functions, no matter what size triangle it is in. Here's two triangles, and they are drawn and labeled appropriately. They are 30, 60, 90 right triangles. And the one on the right is a scale factor of 2. Okay, it's twice as large as the one on the left. Let's pick an angle, and let's find a trig function. Let's do the sine. And let's work with the 30. I don't have to work with the 30, but I'm going to. Let's try that. Okay, let's find the sine of 30 in the small triangle. What did we say the definition of sine is? It's what? Divided by what? Yeah?
Opposite over hypotenuse.
Opposite over hypotenuse. What's the opposite side from the 30 in this triangle? 1. And what's the hypotenuse? 2. So the sine of 30 is a half. Now let's find the sine of 30 in the big triangle. What's the opposite side of the 30 in the big triangle? Yep,
2.
2. And what's the hypotenuse in the big triangle? 4. And 2 over 4 reduces to a half. So the sine of 30 is always a half, no matter what size triangle you draw. And that works for any angle. I just picked 30. All right. So any questions on this idea? That if you have two triangles and all the angles are congruent, that means the triangles themselves are similar and they have the same trig functions, same values. So how do you find all 6 trig functions if I give you one of them like that? Well, if I tell you that the sine of something is 5/6, what 2 sides have I just told you? Yeah? I've told you the opposite and the hypotenuse. So I've given you 2 sides. Once you know 2 sides in the triangle, how can you get the third one? Yeah? Right, we can just use Pythagorean theorem. And that's basically what that says. So if I give you one trig function, take that information, use it to label 2 sides. Could be the opposite and the adjacent that I give you, could be the adjacent and the hypotenuse, opposite and adjacent, but you're going to have 2. Once you label the 2, use the Pythagorean theorem to solve for the third side. And now you have all the sides and you can figure out any trig function you want to know. So let's try using that on this one. All right, so it says the sine of theta is 5/6. So the first step is draw a right triangle. Theta is one of the acute angles. It says it right in the problem. Does it matter where you put the theta? What do you think? Yeah? No. It's going to change how your diagram looks, but as long as you still label the opposite and the hypotenuse appropriately, you can put the theta anywhere you want. You can draw your triangle this way if you want. It doesn't matter. Okay, the picture is just so we can visualize opposite, adjacent, and hypotenuse. So let's put theta there. So now, can somebody explain to me where the 5 would have to go? Now, because of where I put theta, we don't have any choices. It has to go in a certain spot. Yeah? It's the height. So 5 is the height. The 6 is the hypotenuse. And now, to find all 6 trig functions, we need the adjacent. We could do 2 trig functions with just those sides. But to do all 6, we need the adjacent. Can someone set up my Pythagorean theorem for me using the 5 and the 6? Yeah.
5 squared plus b squared plus 6 squared.
Yep. So 5 squared plus b squared equals 6 squared. Excuse me. Okay, so we get 25 plus b squared equals 36. So b squared is going to give me 11, which means b is, as an exact answer, what is b? Yeah?
Square root of 11.
Square root of 11. Now, I'm just going to do it over here because I have more space. I'm going to write all my trig functions. Now, one thing I do not know is the angle. That's fine. I'm not looking for the angle yet. I'm just trying to describe different trig functions of the angle. I'm not describing the angle. Cosecant, secant, cotangent. Okay, let's start with the sine. What's my sine going to be?
6.
5 over 6. Okay. How about my cosine? Yeah? Yeah, go ahead.
Square root 11 over 6.
Square root of 11 over 6. And how about my tangent? Yep.
5 over square root of 11.
5 over the square root of 11, and then when you fix that so the root's not in the bottom.
5 square root of 11 over 11.
Perfect. So yeah, if you do end up with a square root at the bottom, we gotta fix that. So that's what we started with, and then we fixed it. All right. Now, what am I going to do with all 3 of those to get the next 3? Yeah. Just find the reciprocal. So that one's fine because there's no roots in it, so we don't have to worry about that. But what about my secant? Final answer, no root in the bottom. Yep, Patty?
Would be 6 times the square root of 11 over 11.
6 square root of 11 over 11. And now cotangent, well, we've got 2 different things we could flip. If you flip the right one, you're going to be done this in one step. So what would the cotangent be? Yeah,
Square root 11 over 5.
yeah, square root of 11 over 5. Much easier to flip that one than the one we fixed because the one we started with had the root in the bottom. When you flip it, it goes to the top and you're done. Those are your 6 trig functions for that problem. Questions on that? Okay. All right, so let's do this one. What's my first step on example B? Yeah?
Get the hypotenuse length.
Yeah, I get the hypotenuse. Does anybody know what the hypotenuse is going to be in this one? Yep.
13.
13. That's a very special situation. Does anybody know what you call when you take into account all 3 of those sides, that they're not decimals in a right triangle? Yeah? That's a Pythagorean triple. There's an infinite amount of Pythagorean triples. 3, 4, 5 is another one, 5, 12, 13. It's just when all the sides come out without any decimals, they're integers. Let's call it a Pythagorean triple. And it makes all the answers nice. So sine, cosine, tangent, cosecant, secant, cotangent. All right. So this time they didn't give us a trig function. They gave us a diagram. So we gotta write all 6. What is my sine? Call?
5 over 13.
5 over 13. Yeah. Okay. How about my cosine? John? 12 over 13. And my tangent will be, yep,
5 over 12.
opposite over adjacent is 5 over 12. And to get the other 3, just take the ones we have and
Flip them.
flip them. So 13 over 5, 13 over 12, 12 over 5. Any one of those pieces of information could be used to help me find the angle. Like if I wanted to actually know how big the angle is. That's going to be tomorrow. Questions on that? Okay. So now it says to somehow use that diagram to find the 6 trig functions at 45 degrees. I haven't labeled any sides. So now you need to build your own triangle, kind of like they started you off with in that problem. And you might think, well, how am I going to figure out that? Well, they've given you angles to work with. A 45, and a 90. What do you know about that triangle? Yeah?
Just a right triangle.
It's a special right triangle. Okay. What else do we know? Yeah?
The opposite and adjacent are equal and the hypotenuse is
Yeah, there's a special relationship between the sides in a 45, 45, 90. You need to make your own 45, 45, 90. But does it matter how big or small your 45, 45, 90 is? No. Doesn't matter the size of your triangle. You're going to get the same answers. So I would pick numbers that would make this easy to figure out. Because it's a 45, 45, 90, it's isosceles. What would be a good length we could use for the legs? You technically can use any number you want. Yeah?
1.
Yeah. So if we make that a 1 and a 1, now the hypotenuse cannot be any number you want. It has to be based off the lengths you just picked. What would that make the hypotenuse in this 45, 45, 90? Square root of 2. Okay. Again, that's not the only 45, 45, 90, but it's one that will work. And it's probably the simplest one. So now we can do our trig functions. Sine, cosine, tangent, cosecant, secant, cotangent. Okay, and we're trying to find the 6 trig functions of 45 degrees. So should we do everything from the angle in the lower left or the angle up at the top? What should be my perspective? Yeah?
Your perspective doesn't matter here.
It doesn't matter, right? They're both 45-degree angles, so pick any one you want, you're going to get the same answers. Let's do everything from the perspective of that one. All right. What's the, and actually I didn't even need to write theta here. I could have actually filled in 45 degrees, because that's what I'm really doing, the sine of 45 degrees. Okay. I'm not going to erase them all, but I'll just put it above it, so you know it's 45. Okay. What's the sine of 45 degrees? Yeah. So let me think. Yeah, opposite over hypotenuse, 1 over root 2, and that turns into root 2 over 2. Perfect. Okay. What's the cosine of 45 degrees? Same thing, because the opposite and adjacent are the same. What's the tangent of 45 degrees? Yeah? 1. So that makes the cotangent 1. And when you flip root 2 over 2, what do you get? Yeah?
Square root of 2.
Just square root of 2. Okay. And there's your 6 trig functions for 45 degrees. Right. Now, let's do the same thing, but let's look at, I'm not going to do the 6 trig functions of 30 and 60. Let's just do 30. And I've given you a hint. You've got to create your own 30, 60, 90 right triangle. I'm not giving you one. Doesn't matter how big or small you make yours, but you do need to label the sides correctly. Tell me about this triangle. Yeah?
And a right triangle.
Nope, it's not a right triangle. Okay. What else do we know about it? Yep.
It's an equilateral.
Okay, it's equilateral. So what does that tell me? Yep.
All the interior angles are going to be exactly the same.
Okay, and if all of them are the same, we could figure out that value. Yep.
60 degrees.
They're all 60 degrees. Okay. But in order to do trig, the way I'm showing you, you need a right triangle. So, any thoughts about what we could do? Yeah.
Split it.
Yeah. There's different ways you can prove this, but from geometry, if you draw a line from the vertex perpendicular to the opposite side in an equilateral triangle, it will split it into 2 congruent triangles. We're not going to get into the proof of that, but it's very easy to prove. So we now know that this is a 90, that's a 90, and I know one other thing now. Yeah?
Each of the top angles are 30 because you split that 60 degrees in half.
Yeah, that's a 30. So now let's focus on this triangle and see if we have enough information to label all the sides. What is the hypotenuse of that red triangle? Yep.
2.
2. How long is the bottom side? Yeah. Has to be 1 because we split this side into 2 congruent pieces. So the only way you can take the number 2 and split it evenly is if each one of them is 1. And if you use Pythagorean theorem, you could figure out that your height is the square root of 3. So there's your sides. Now, just make sure you put the labels in the right spot. That's a 60. That's a 30. And you know what? I'm just going to do the sine, the cosine, and the tangent of 30. That's really enough for now. So sine, cosine, tangents. I think we did the sine of 30 earlier when I was showing you similar triangles. What's the sine of 30? Okay.
Is it like that?
Yep, sine is a half. What's the cosine of 30? Yeah,
Root 3 over 2.
root 3 over 2. And how about the tangent of 30? Yeah.
2, right?
Yeah.
Isn't it 2?
The tangent of 30, no, it's not going to be 2. 2 would be the cosecant. Yeah.
Is it root 3 over 3?
Let's see, so it's adjacent of a hypotenuse, which is 1 over root 3, which turns into root 3 over 3. Yep. So there's your 3 trig functions for 30, and then if you flip them, you could get the cosecant, secant, and cotangent. Any questions on flipping it, especially when you have to fix the root? We did a lot of the root stuff back when we did unit circle. So. Okay, so last page. All right. Complementary. What? To remind me, what does that mean? If 2 angles are complementary? Yeah.
They add up to 9.
They add up to 90. How come in a right triangle, the 2 acute angles always have to be complementary? Kind of already talked about this, I think. Yeah.
It's already 90 degrees in there, and the triangles, the two angles have to add up to 180.
Yeah. Yep. So if you have a right triangle and you've already used up 90 there, then angles 1 and 2 also have to add up to 90. And if they add up to 90, that means they're complementary. Yep. All right. So now we're going to start labeling the triangle, but we're also going to label the angles. We don't normally use 1 and 2. Okay? We use Greek letters to label the angles. And the reason that I'm going to stick with using Greek letters is because it differentiates it from a side. Okay? Some books you might see capital letters for the side, or a capital letter for the angle, and then lowercase letter for the side. Right? Then I think it starts to get confusing. Because then you got to remember, wait, is the side the capital letter, or is the angle the capital letter? And then some capital and lowercase letters look the same, depending on the letter you pick. So then that's another problem. And it just gets confusing if I ask you, like, what's C? And if you don't know, well, wait, does he mean capital C or does he mean lowercase c? It gets confusing. So we're going to always stick with using Greek letters to represent angles. And that's what we've been doing all along. Alpha is always going to go across from A. And what's that one at the top called? Yeah.
And beta.
Beta is always going to go across from B. With right triangles, you do not need a name for that one because it's always the 90. When it is not a 90, which we'll do at some point, we'll need a name for it. But for now, those are the only 5 things you need. A, B, and C are the sides. Alpha is across from A. Beta is always across from B. And it doesn't matter how you draw your triangle. You can draw it like that. If you put A down there, that's fine. Put alpha up there. A and alpha have to be opposite. All right, so now I want to take that diagram and I want to find some trig functions. Let's do the sine of alpha. It's not going to be numeric, it's going to be algebraic. But in that triangle, what would the sine of alpha be? Yeah,
A over C.
it would be A over C. Now I'm going to find something different. I'm going to put the word co in front of that. That turns it into cosine. And instead of using alpha, I want to use the angle in that diagram that is complementary to alpha. What angle is complementary to alpha in that diagram? Yeah.
Beta.
Beta. So I did 2 things to make up a new problem. I put the word co in front of the trig function, and I took the angle that was complementary to what I started with. Let's find that. What's the cosine of beta? What's the adjacent over the hypotenuse? Yeah?
A over C.
It's also A over C. So those 2 things are exactly the same. Let's try another one. Tangent of alpha. What is the tangent of alpha in that diagram? Yeah, that's A over B. All right, so now let's make up a new problem, and let's do 2 things. What trig function do you get if you put the word co in front of that one? Yeah,
Cotangent.
you get the cotangent. And what angle is complementary to alpha? Yeah, beta. Okay, let's find the cotangent of beta. So from beta, I need the adjacent over the opposite. What is adjacent over opposite? Yeah, it's A over B again. Okay, so hopefully you're kind of noticing a pattern. And this pattern is called the complementary angle theorem. And what the complementary angle theorem says, that if you have 2 functions that are cofunctions, and you have angles here that are complementary, they will come out exactly the same. Okay, so you need 2 things. You need to have cofunctions, and you need to have angles that are complementary to each other. So for example, let's try something numeric. Based on the complementary angle theorem, what is another way that I could write the sine of 15? Yeah?
The cosine of 75.
The cosine of 75. Those 2 things are exactly the same. So what is the sine of 15? Well, I don't know that. But I know it's the same as the cosine of 75. All right. How about the tangent of 30? What would that be the same as? What's another way I could write it? Yeah?
The cotangent of 60.
The cotangent of 60. So why would you want to rewrite it? Well, that would help you to figure out something like that. I want to know what the sine of 35 minus the cosine of 55 is. And what I would be more interested in here is the reason. That's what I would ask you. Because anybody can just type that in and get the answer. But I want to know how you could do it without a calculator, especially with a sine of 35. It's a pretty awful number. It's going to be an irrational number that I don't know off the top of my head. But anyone have a guess what that comes out to? Yeah.
0.
Yeah. Why does that come out to 0?
Because sine of 30, or 35 plus 55 is 90.
Okay, so these are complementary. And what else?
Sine is, you put co before sine, it's cosine.
Can you say that again?
You put co before sine. it's
Yeah,
cosine.
these are co-functions. So there's 3 pairs of co-functions: sine, cosine, secant, cosecant, tangent, cotangent. Those are the pairs of co-functions. Sine and cosine are co-functions. 35 and 55 are complementary. That means each thing there that I'm subtracting is equal. If you subtract 2 equal things, you get 0. How about this one? Tangent of 20 divided by cotangent of 70. Yeah?
Would be 1,
Yeah. How come that would be 1?
because it's like dividing a number by itself.
Can you explain, though, why it's dividing a number by itself?
Because they're co-functions.
These are co-functions, yeah.
The numbers are complementary.
And those are complementary. Because it meets those 2 criteria, the expression in the top and the bottom are exactly the same. If this was the tangent of 21 divided by the cotangent of 70, nope, doesn't work. Okay, so it works with subtraction and division. Subtract 2 things that are the same, you get 0. Divide 2 things that are the same, you get 1. How about if I add 2 things that are the same? What do you get if you add 2 things that are the same? Yeah?
Just double that amount.
Yeah, you get that thing doubled. So, well, what does that mean your answer would be? Well, then it depends on the original problem. So this theorem doesn't really help you with addition. And how about multiplication? If you multiply 2 things that are the same, what do you get there? Yeah?
Just the whatever you had squared.
Right, you get whatever you had squared. It's not like dividing 2 things, you will always get the number 1. Right? So you don't really get a nice number unless you're doing this with subtraction or division. Any questions on that? Okay. So that is the homework for tonight. They're on page 361. And then I added 2 questions at the bottom involving the complementary angle theorem.